So this is the video that goes with the second lecture in Chapter 8 on the McGraw-Hill textbook. We've talked about single, double, and triple covalent bonds. Remember, co means sharing, valent means outside electrons. Two atoms that are both nonmetals that are very close to each other on the chart are going to be close in electronegativities. They can't win the battle of I'm going to steal your electrons, no, I'm going to steal yours, so they end up sharing electrons. Different than ionic, but they do it for the same purpose. They do it to be stable and have full orbits. Even though they're sharing, they end up with what they consider, what they feel like is full orbits. So today we're going to talk about the types of bonds. Now there's a lot of different ways to spin that and say, you know, double, single, triple, those are types. But specifically, the actual bonds that happen can be called pi or sigma. A single bond is always a sigma bond. Think of the sigma bond like being that low road that goes along the river, and you've got kind of a canyon up here. It's the easy road, and it's maybe the road you want to be on because it's scenic and it's down there by the river. But when that floods, you can't be on the low road. You might have to go up on top of the canyon and take the alternate route. Well, that's kind of pi and sigma bonds. The sigma bond would be the straight line where electrons like to be because it's the easy trip. Kind of like going to a local town, you go straight there. But if the road's closed, you have to take a detour. So there's an alternate route, which would be the pi. If there's a sigma bond and there's there's electrons that want to make another bond, they have to do a pi bond, which is a circular bond where they go around the outside, kind of like the top of the canyon. You have to walk there. Now, if you have a single bond, you know, on the level of single and double bonds, if you have a single bond, it's always going to be a sigma because straight line is the easiest and lowest energy bond. If you have a double bond, you can't have two sigmas, so you have one sigma bond straight in the middle, and then you have a pi bond that's kind of a circular route where the electrons go from one atom to another around the outside, and then from that atom back again through the outside on the other side. Now, if you have a triple bond, you can't have two or three sigmas. You have to have one sigma, and then you'll have one pi bond going around like the side, and then another pi bond going around the top. That's the only way you could have three bonds. You're going to be asked to identify how many pi and sigma bonds are in this compound. Very easy. Look at the single bonds, and they're all sigma. For a pi bond, or for a double bond, the second bond's always a pi bond, but the first bond's a sigma. So if you're going to count in a compound, go through and count every bond one time, and that's how many sigmas. Then go to the double bonds, and each double bond, the first bond after the sigma is a pi. If there's a triple bond, that's made of one sigma and two pi. So that's how you go through the compound and count up your pi and sigma bonds. Remember, if there's a single bond, it's sigma. Think of S for sigma, S for single. That's the easiest way. Every bond in a single bond is a sigma. After that, you could have one pi bond and a sigma to make a double, or one sigma and two pi bonds to make a triple. There are no quadruple bonds. It's too high of energy, and there's not enough room for the electrons to maneuver. So keep that in mind on page 246 in the McGraw-Hill book. There is the actual appearance of sigma and pi bonds, what they look like. So you know, keep in mind you'll be looking at an actual structural diagram, and I'll ask you how many sigma and how many pi. Again, count every bond once because the first bond's always a sigma. After that, go find the double bonds and triple, and everything beyond the first sigma bond is going to be a pi. So that's how you'll be doing that. Bond strength and length. So first of all, a single bond is the longest, double's a little shorter, triple bond is the shortest. Strength is kind of the opposite of that. You would think that if you had three bonds, it's going to be stronger. It is. If you add 2, that would be weaker than the triple bond, but stronger than the single bond. So they're kind of in order 1, 2, 3, with 3 having the highest strength. And there's a chart in your book that has the actual bond lengths for different types of like carbon and nitrogen and oxygen and oxygen. Tells you the different lengths and also how much energy is put into the bond. The amount of energy that's put into the bond is how much energy it would take to break that bond. So if it told you 637 kilojoules per mole, then you would count up how many bonds like that you had, multiply by 637. That's how you figure out the amount of total energy. When we talk about more than 1 mole, once you get the energy in 1 mole of the compound, which is what the chart has, you just multiply times 2 moles, 3 moles, 4, whatever the problem says that you have. So look for that bond energy chart. You'll have some practice problems like that. There's some on your review. Look up the particular bonds that you have, write down the energies, and then add up all the energies and all the bonds, and that's how much energy to break the compound down totally and break all the bonds. While we're talking about energy, when we do reactions, sometimes you'll have heat emitted, sometimes you'll have heat absorbed. How do we know what's going on? Well, if you touch it and it's hot, it's exothermic. It's releasing heat. Heat is exiting. If you touch it and it's cold, then it's taking heat from your hand. That's why you feel cold. And endo means heat's going into the reaction to make the reaction go. Endo and exothermic, important words. We'll use those all year. Make sure you know those. Now we're going to talk about naming compounds. And, we've already named ionic compounds. You remember that we had the stair step, and, the nonmetals are to the upper right, metals are all to the left. The way we remembered ionic compound is ion both sides, a metal and a nonmetal. Okay, ion both sides, ionic. Crisscross, like your arms, crisscross, to write the formula, never use prefixes. Well, so we're going to be in molecular compounds now, and you're always going to use prefixes for molecular. The reason is that we don't crisscross, and there's more than one possibility. Everybody's familiar with carbon dioxide. Well, you're probably familiar with carbon monoxide too. 2 different carbon oxides. And we don't crisscross to write the formulas, so there's more than one way from the form. Carbon monoxide has a triple bond. Carbon dioxide has double bonds. So it's different ways that it can come together. So you have to tell people how many of each atom you have. That would be why we use prefixes for molecular compounds. The way to remember this is to look at the chart and say 2 nonmetals. Notice my arms aren't crossing, so there's no crisscross. So 2 nonmetals, and then we, yes, use prefixes. And if that doesn't work for you, find some way that does, but you need to remember that molecular compounds always have prefixes. And we're going to look at these prefixes. They're here on your notes. 1 for mono, 2 for di, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa, 7 for hepta. People miss that one a lot because it's not one you use. 8 for octa, 9 for nona, 10 for deca. Make sure you go over those because we'll be using those the rest of the year, especially in this chapter. So one extra deal, I told you always use prefixes. If the first element or first atom has a 1, you don't have to say, for instance, carbon monoxide. You could say carbon monoxide, or you could say monocarbon monoxide. It's just a little clunky to say that extra first prefix, and it's understood if you don't say a prefix on the first one, it's 1. So you could leave off the first prefix only if it's 1. Don't leave off the second one. You always have to say the second prefix. So CO, carbon monoxide. CO2, carbon dioxide. N2O5, dinitrogen pentoxide. Use prefixes. Now, prefixes can be your friend here because if I give you a compound name and it says dinitrogen pentoxide, well, you know that you've got 2 nitrogens and 5 oxygens. It tells you. So it actually can be easier to write these formulas. So Remember, molecular compounds, always use your prefixes. So we've talked about naming acids already in the last chapter because they generally behave like ionic compounds, so we covered them in the ionic compound chapter. There are 3 rules. The easiest way to remember this is try to focus on the first rule first. Rule 1, remember you always have H's for your acids, and we'll learn some acids later on that don't have H's, but for right now, all the acids you deal with will have H in the first slot. If there is an H by itself in the first slot, not Hg for mercury, but H, then it's going to be an acid unless it's H2O. And water can behave like an acid. It's a kind of a special compound, but we don't name it like acids. So, looking at formulas, always look, see an H, you know it's going to be acid. Maybe write acid right above so you remember to name it as an acid. If it has an H in the first slot and it has 1 capital letter with it, then it's rule 1. That's that easy. Rule 1 always fits this mold of hydroblankic acid. So, and other than a couple of exceptions, cyanide is one of them, the compounds that are H and 1 capital letter are going to have an anion, a negative ion that ends in "ide." And it generally comes from the metals, the nonmetals, above the stair step. So, HF, hydrofluoric acid. HCl, hydrochloric acid. HBr, hydrobromic acid. HI, hydroiodic acid. If you see 1 capital letter, hydroblankic acid, where the blank is the root of the element involved. If you're seeing the name and you're writing the formula, if you see hydro, well then go to the periodic table and look above the stair step. If it's hydrochloric acid, then it's H with Cl. Remember, rule 1, H with 1 capital letter. What if it has 2 or 3 capital letters? Well, then you go to rule 2 or 3. Rule 2 would be from the polyatomic ion chart. Rule 3 comes from polyatomic ion chart. 2 would be the low number, and it's the low rule. Ite from the polyatomic ion chart is the low number of oxygens, and we use us to name those. So SO3 with an H, H2SO3 would be sulfurous acid. H3PO3 would be phosphorus acid because it's the low oxygen. The high oxygen for SO4 with hydrogen, H2SO4, because we crisscross the 2 from the sulfate, H2, the 2 comes from the 2 minus on the sulfate. H2SO4 is sulfuric acid. High number of oxygens, the 8 ending, the ic acid, rule 3. So we've gone over those already. You should know them by now. Review over them. Make sure that you know how to use those rules. So we're going to talk about a couple of special types of bonds now. One of them is called a coordinate covalent bond. And the easy way to remember this, I think, at least this is how I remember it, is coordinate has 2 O's. Should make you think of 2 electrons, 1 compound, okay, the 2 circles, 2 electrons, 1 compound gives both electrons in a shared pair. And how do we know when we're going to see this kind of example? Well, when you are doing your dot diagrams, remember we put 2 elements side by side, and then we share an electron. Okay? We share another electron, and we share another one. We keep going until there's 8 around both. Unless it's hydrogen, then it only gets 2, right? Because the first ring just has 2. Until it fills its orbits. Well, when we do something like carbon monoxide is a good example for this. We have CO. Carbon is in 4A, 4 dots. 1, 2, 3, 4. Oxygen's in 6A. 1, 2, 3, 4, 5, 6. We're not happy. Let's share another one. We've got 1 shared, so we're going to pull 1 here and 1 here, put them in. Now we've got 1, 2, 3, 4, 5, 6. So there's 6 next to 1, 2, 3, 4, 5, 6, 7, 8. We're done with the oxygen already. 6 next to 8 should be that alarm that goes off. Ding-a-ling-ling-ling-ling-ling. Oh, that's coordinate covalent. Okay, so you know that it's going to have 2 from the one that already has 8 is going to give both of the electrons to this other pair. We couldn't share one from each side because now we'd end up with 7 and 9. This one doesn't want 9. It wants to stop at 8. It already had 8. So it doesn't mind giving both of them. Kind of like you go into the lunch hall and your buddy is 50 cents short, but you got 50 cents extra. So you say, sure, here's 50 cents. Now we can both eat. That's what they're doing here. The oxygen's the one that's given the extra. For that last pair, it gives both of the electrons. So when you see 6 next to 8 and you feel like you're done and you're puzzled, always think coordinate covalent bond. Now, the oxygen gave both of them. We have a special symbol for that. We draw an arrow for one of the structural diagrams, and that arrow tells us that oxygen gave both of them. And that means coordinate covalent. And when it's done, it's just like any other triple bond. It's just how it forms that's different. Polyatomic ions. Well, the way to do polyatomic ions, just like any other ion, especially negative ions, which is most of the ones we're going to do, how does an atom that's neutral become stable? Like fluorine or chlorine or bromine. They gain electrons. Well, it's the same thing if we have OH, and with O having 6 and H having 1, do the dot diagram for it. You'll see O ends up with 7 and H with 2. So the hydrogen's good. It's happy. It's got a full orbit. But the oxygen's only got 7. And there's no more electrons. It can't share and do coordinate covalent because hydrogen's done. It only needs 2. So how do you get the electron? You pull it from a sodium or from somewhere else, some atom that wants to give one. You pull it in. We put brackets around it and say minus, and then you're going to make that dot a different symbol like a triangle, so I know that that one came from a different place. And that's what I always say is make it a triangle, because that way I know that you know what you're doing because we've talked about making it a triangle. If you just make it another dot, if the instructions say that you need to make your gained electron a different symbol, then you're going to lose some points. Make it obvious that that one came from somewhere else and make it like a triangle or a star or something like that. So that would be polyatomic ions. Now, you're going to have one or more polyatomic ions on the quiz, and you're definitely going to have a couple of them on the test. So go through and pick up things like SO3 2 minus and SO4 2 minus, and some of the obvious ones. OH, definitely an obvious one. Do the dot diagrams for them and see how you have to add 1 or 2 electrons to make the orbits full. That would be polyatomic ion covalent bonding. And when we get through, you're going to put brackets around it and a charge. The charge is equal to the number of electrons you gain, negative. So there'll be some practice for that. You'll have some on your review. Try them out. Make sure you don't wait till the test or the quiz to see if you know how to do them. So that covers the second day of notes. We are going to work on our molecular model lab. All that's on the mid-table. So work on your review. Try to get done some of the things we went over. And good luck.